Anyway, so I'm going to talk about the tuned vibration absorber a little bit first, just because this is something that we know in mechanical engineering, but since we have a more broad audience, I'll introduce it, and then I'm going to talk about, I'm going to generalize it and extend it to applications and so forth. But basically, you're interested in a resonance problem. So in electrical engineering, you think about an LRC circuit, but we have a simple mass spring system, and as you sweep this driving frequency, you get a resonance peak if you look at the amplitude of response. So one way to suppress this resonance is that if you're operating at a frequency here, you can add another degree of freedom that's tuned, that has an isolated natural frequency omega n, and it turns out that when you drive this mass and at the frequency, the natural frequency, this guy can actually sit pretty much still, and the oscillations of this thing, the force through the spring will cancel, and so if this is the response of the primary mass, it essentially is it's near zero, and with no damping and so forth. And so this is a tuned vibration absorber. So the idea is this thing you care about, some part of your car or something, and you reduce the vibration, and this thing wiggles around. And that's what I'm going to talk about, a torsional version of it. But it turns out that if you want to get a wideband response, you need to put damping in here. This is a problem solved by Den Hartog, how to pick these parameters optimally to do a min-max optimization of the response of this. And this has been known. We teach this in the undergrad vibrations class. And in fact, these dampers exist. This is Type A 101. And this damper here is just a big pendulum suspended. And in fact, it's probably the only vibration absorber that has its own mascot. You can get your picture taken with the damper baby, they call it. And this thing is tuned to the first natural frequency of this building so that under an earthquake, this thing will be dominated by its first mode, which is at 0.15 hertz, and this thing will swing instead of the building swing. And so what I'm interested in is a problem where instead of one absorber, you have multiple masses that make up the absorbers. And I'm going to assume them to be identical. And if you look at this system, it turns out that it has some vibration modes. So these are just the eigenmodes of this thing. And it has two modes that look like the single mass absorber system, where these modes are essentially omega 1 and omega 2. And in this case, it looks like this system has just these two frequencies. But then, since it has n+1 degrees of freedom, there's n+1 vibration modes. And the other n+1 modes are essentially modes where these things oscillate. And the sum of the forces caused by these on this big mass are zero. And these are degenerate modes. They all have the same natural frequency. You have n-1 of those. So, and now if you drive this thing, it's interesting because the driving is orthogonal to all of these modes. And by the way, if you look at these modes, they're degenerate in the sense that you just find n-1 vectors that span this n-1 dimensional space, and any of those will do with the eigenmodes. You pick them for convenience. But the point is that the forcing is orthogonal to these guys, and it will only excite these two modes in the idealized system. And I'm going to talk about a torsional version of this system with nonlinearities. And so before I get to that, though, if I were to remove the spring to ground here, which is the version I'm going to talk about, this thing has a so-called rigid body mode where you have a zero frequency, the whole thing can just translate. And then if I add nonlinearities to these springs, and it turns out that you can eliminate, by looking at the acceleration of this mass, you can actually, and you use a relative coordinate z, which is the difference between x and u, you can write down an equation where you essentially have a set of n resonators with damping, linear, nonlinear springs. They're all this actually comes from the acceleration of this mass. It's the base excitation seen by all these guys. And you also have the forces from all the absorbers acting through back on each individual absorber. And so with this summation, you end up with global all-to-all coupling in a mechanical system. So this system has n identical resonators, weak coupling. The weak coupling comes from this parameter mu, which is the ratio of the mass of the absorbers to the primary mass, and that's small in applications. You have this problem, this symmetry we'll talk about, and it turns out that it's driven so that this frequency is close to the natural frequency, and these systems are lightly damped. So all kinds of things. For those of you who do dynamical systems, it's right for every kind of interaction that you could imagine. So, and in fact, when you do this decoupling, you're essentially taking a system like this, and through this decoupling, you're coming up with a system with where the absorbers are all coupled to one another. Now, the application I'm interested in is going to be a torsional application. So if there's a little cartoon of an engine, and if you look at the torque versus crank angle, this is for a 4-cylinder example. Each cylinder has a firing pulse, and then it's essentially zero. There's a little negative pressure when it's taking in on the intake. But essentially, you take these 4 pulses and look at them on the crankshaft, and this is over 2 crank revolutions, and you sum, and you actually get a nice thing that's pretty close to a harmonic. This DC term is what you think of, so if your engine's rated at 100 foot-pounds or how many newton meters, that's this. But you get a fluctuating part. And actually, I've shown it negative here, and it turns out that if you drive a stick shift and say put the car in second gear, drive a 4-cylinder engine and let this clutch out, your torque will actually fluctuate and go negative on part of the cycle. That's how big the fluctuations can be. This fluctuating torque is what we're going to focus on. And again, in multi-cylinder engines, it's very close to harmonic. So I'm going to talk about these torques, and they depend not on time, but on the crank angle. And they depend on n times the crank angle. For an engine with n cylinders, 4-stroke, this excitation, is number of cylinders divided by 2. So you look at the 4A components, again, this is in crank angle space. So I'm really interested in this torque, and that's a torque on the crankshaft. Now, why would you be interested in this torque on the crankshaft? It turns out that, Richard, you still fly light airplanes?
Yeah.
So your engine, I'll bet, in some kind of a PO6 engine or something, is it?
I don't know.
Okay, but it probably has some pendulum absorbers on it, because what happens is in an airplane, you have this big propeller, which is a huge inertia, and you have these torsions that happen from the cylinders firing, and there's a gear between those, and that thing will get beat up unless the crankshaft is putting out a smoother torque. So these pendulums that I'm going to talk about exactly do that, and they've been around in aircraft engines for years. But what about cars? Well, here's a thing, in case you don't follow it. In Michigan, this kind of stuff is headlines. So the CAFE, corporate average fuel economy, by 2025, the corporate average is supposed to be 54.5 miles a gallon. Politically, that'll never survive. That's what the target is. So what does fuel economy have to do with vibrations? Well, it turns out that if you think about a torque converter, so these are things I've worked on, Chrysler and the Ford. Torque converter, is nothing more than a viscous coupler that decouples the engine from everything else when you're sitting at a traffic light with an automatic transmission. And it's a lossy device. So what happens is and you can lock the torque converter up when you're driving down the road at 35 miles an hour, it locks up with a solenoid. The conditions under which that can happen depend on the torsional vibrations of the engine. If you can widen that envelope, essentially in terms of RPM, you get about a 1% fuel savings per 100 RPM. And right now, Chrysler is looking at about 500 RPM reduction in torque converter lockup. That's a serious number. The other thing, and this really is related to what we call lugging operation, which is low speed, high torque operation. Basically, if you can run an engine at a low speed, you have fewer pumping losses, less friction, and in fact, if you look at the fuel burn rate, that's this contour map, and this is engine speed and the mean torque level. And basically what happens is, if you can run at lower speed, you burn less fuel, and it's just due to these efficiencies. And so like our minivan has an economy button on it. My wife doesn't like it. Why? Because it runs a little rougher when it's in economy mode, because it changes the shift schedule so that you're running down here more than up here. Another case is variable displacement engines, and I'm going to talk about those. Yeah.
If you want to be efficient in your car, you lug your engine.
Yeah. Yeah, it vibrates like crazy. I'm going to here, and here's an example of why, and lugging just isn't generally acceptable. But I should say that engines are going to smaller displacements, higher torques, where these torsionals are important, and that's why I get money from the car companies. But here, lots of companies use variable displacement. Chrysler, GM, Honda. Honda's is a V6, but here's the idea. You have a V8 engine. When you need the power, you run it full cylinder. V4, you run it reduced cylinder. The way you do it is you have these actuators on the cam. I could talk more about it, but you essentially close off the valves, don't send fuel to those cylinders. And so this is a very nice application that will continue to exist, I think, for large scale like trucks and so forth. When you need torque, you get it, but when you're cruising along, you don't have to use all the fuel. But here's the reality, is that if I look at the engine speed versus torque, and what happens is, again, if you run the engine faster, you can get more fuel in, and so the torque, this is 100% torque, but then these losses take over and it dips back down. So this is a schematic of what happens. If you're in V4 mode, you can get about half that. There's a bandwidth on the actuation limit, how fast you can activate, deactivate cylinders. So you have, if you're running really fast, you still have to stay in V8 mode. And at the low end, this thing is deactivated purely because of a vibration limit. So for example, Honda Odyssey minivan will not go below, I think it's 1200 RPM. As soon as you're sitting in a light idling, it's in full cylinder mode, purely because of vibration. But you can get a couple miles per gallon if you can get down in this range. So how do you reduce torsional vibrations? Well, you can add flywheels. Bad idea. Nobody wants inertia, nobody wants mass. There's torsional dampers, these things called harmonic balancers, they're lossy. You can have, there's things called the dual mass flywheel, these are available in cars. But the thing I'm going to talk about is centrifugal pendulum vibration absorbers, which have some very interesting features, and the most important of which, and now see my cartoon isn't even working here, my movie. This thing's supposed to be swinging back and forth. And these are two pins that ride on these green rollers relative, this is supposed to be the crankshaft, and these surfaces, so the center of mass follows a path. The beauty of this is, and the key difference between this and a regular tuned absorber I talked about is that this is driven by centrifugal effects, which in its natural frequency scales like the engine speed. So if you think about that torque that was n times theta, well, if theta is roughly omega t, that means the driving frequency scales with engine speed, and this is, say, the driving frequency, and so you can tune this absorber so that it scales. So you can, if you line these two lines up, this thing stays tuned at all engine speeds, whereas these harmonic balancers are essentially mass spring systems. That, and there's a cartoon that doesn't work, but these things have been around. Here's a top view of a Sikorsky helicopter with 4 of these pendulum absorbers. This so-called bifilar suspension is interesting. 2-point suspension essentially allows the mass to translate and not rotate relative to the primary. And so you get, and the other thing is it allows you to change the path of the absorber. This is a crankshaft we worked on with Ford about 15 years ago. But these things have been around for years. Light aircraft engines, World War II, people were really, really interested in these things, and it's fuel economy, it's making automotive interest. So here's a simple cartoon of what happens. So you have and I'm going to look at this in a more general way, but essentially we have absorbers whose coordinates are given by S's. We have a rotor whose coordinates given by theta. We have this oscillating torque that's ordered torque, and essentially the absorber frequencies. This is a great little exam problem to give to undergrad dynamicists, because this point is accelerating. When this rotor runs at constant speed, this point is accelerating there with r omega squared, so you just replace gravity by r omega squared, and you can work out the tuning order, so-called, which is the frequency scaling parameter for the times the frequency. And the applied torque is n, and so basically you're going to worry about one of the key parameters in this design will be n tilde versus n. The big problem comes about because of the swing angle. Basically, this just shows that if you look at the engine speed, these pendulums, when they're locked versus when they're free, that's the measure that you use, because you say, well, of course, you add inertia, you're going to reduce the vibration. But so the benchmark that I always talk about is absorbers locked versus absorbers free. The other thing is that when we talk about rotor torsional vibration, we look at the angular acceleration of the rotor. So you just, if you make that amplitude small, you don't have much, then you're running at essentially a constant speed. So these absorbers, you want to design them. This has been around again for a long time, so I'll tell you what's new. There's been a lot of work on this. But so you want to reduce torsional vibrations at order n, not amplify them at other orders. Of course, this would only happen through nonlinear effects, but these systems happen. You'd like to maximize the range of fluctuating torques, but you don't want to do it with much absorber mass. And of course, these are in exact conflict with one another. And so what's the absorber design problem? The absorber design problem is going to be, so this is my schematic, my cartoon of what I'm going to look at. The absorber design problem is really to design this path, and I can do that by shaping these cutouts of these rollers. And I'm going to have n absorbers, and this rotor spinning at nominally a constant rate, but I'm interested in the fluctuations of this rotor. And this path is going to be specified by this function r as a function which is the radial distance from the center of rotation of the rotor to the position of the mass, and it's a function of this arc length variable.
And it's the path rather than just the curvature, because you want to do large amplitude.
I want to do large amplitude. Large amplitude is very important in these problems. So the analysis outline is get the equation of motion, Lagrange. Then I'm going to do something here this is an interesting transformation. We're going to consider the independent variable. We're going to do a transformation to theta as the independent variable so that the applied torque, instead of being sine omega t, it's sine of n theta. And we want that to look like a driving term. And rather than a nonlinearity, it doesn't really matter, but it allows you to put these in the equations in exactly the form that are, and you scale things. It turns out that the scaling on these things, because they're tuned at all engine speeds, you want them to be lightly damped. Remember that valley? You want them to be lightly damped. You can tune them near resonance. It turns out that if you look at the parameters, say the amplitudes of the torques, when you scale the equations, you scale those torques by the kinetic energy of the whole system. That's a small parameter. You have small damping, small forcing, small inertia ratio, works out the scaling, so you can apply a standard method of averaging, and you can use that to analyze the system. So here's the structure of the equations of motion. It looks sort of like this. So the absorbers have a nice, so and again, I've already changed to theta, so primes are d by d theta. So this looks like a nonlinear oscillator. And if the rotor's running at a constant speed, this is where you get this.
S is what?
S is the absorber arc length variable. This is, it was cap S, now it's small because it's non-dimensionalized. That's all. Y is the rotor angular speed normalized by omega. So y prime is actually a measure of the rotor angular acceleration. And so if the rotor is running at a constant speed, y prime is 0, this term's gone, this is absorber damping essentially. And what you have then is a nonlinear oscillator where F depends on the path you choose. And I'm going to talk a lot about that path. Now when you turn, the torques appear in here, this is theta, this is the driving torque. Epsilon is a small parameter that scales a bunch of things. But this is the driving, and now S, this capital S is essentially the sum of all the effects of the absorbers on the rotor. And this thing turns out, the engine's running at nominally constant speed, so this is small, but I want to make it even smaller by coupling in these degrees of freedom. So here's how you do this reduction in this problem. It's more complicated than the translational one I showed you, but essentially this y prime can fit in here, but while you put y prime in here, you still have y's, but it turns out that y is normalized by the engine speed, so it's 1 plus a small quantity, and you pick alpha differently for different scalings I'll talk about in a second. But anyway, and so you can push all those y terms out to higher order, and so what you end up with is a set of coupled oscillators, coupled resonators, I should say, that have this form. But I want to talk about scaling first, so nice set of coupled. The thing is that what I want to do is I'm going to, and these are physical coordinates and parameters like the inertia, the absorber position, rotor speed, fluctuating torque, absorber damping, not dimensionalized. And there's two different scalings, and I'm going to talk about two different kinds of paths. One is a general path, and you can think of this as the circular path case, simple pendulum. And in that case, the nonlinearities come in very fast, and you have to do amplitude scaling, just like you would for a Duffing equation or weak nonlinearities. But it turns out there's an absorber, the path, where I can actually not worry about amplitude scaling, and I can actually get equations of this form for large amplitude motions. Not arbitrary, but very large amplitudes of swing. And I'll describe that in a minute. But this is back to that case where you have a set of n resonators. Now I don't have frequency edge, I have orders. This thing here is a driving, this is actually, the driving order is represented by this term, it's n, which is approximately n tilde, and and in here, this S, again, you have all the summation of all of the absorbers, so this global coupling. And again, we've seen this picture. Now, one thing that we want is that we are going to want a synchronous response, and you'll see why. So we like this thing. Look at this is my version 2 of the absorber, these are off, but anyway. So this system has a very nice symmetry, and the symmetry is basically as follows. When the system's operating, you can take any absorber and swap with any other absorber in any order you want, you still get the same dynamics. That's that simple. But it's represented by this symmetry group, and basically in the equations it says that, and I represent these transformations as matrices that, by the way, when I got into this, I didn't know anything about, these equivariant dynamical systems and bifurcation, so the first person I called was Tim Healy. And Tim was very helpful. He said, This is the basic bare bones thing, and that's all I've really done with it. But Tim was very helpful in guiding me how to handle these problems. But basically, so our absorber equations abstractly, they're like this. If you have a transformation, some kind of transformation, which in our case is some kind of a matrix, if it satisfies this condition, then this is a symmetry of the equation of motion. In this case, the gammas are elements of this group, of this symmetry group Sn, which essentially allows all permutations. And so this imposes some. We're going to see it has effects on solutions are possible, and if the absorber response is synchronous, it also possesses this symmetry. And that tells you that there are certain types of, when you have instabilities, that there will be certain types of responses that are expected to come out of those instabilities.
Is that the thing called homogeneous of degree 1? Is that the same thing?
I believe so. Yeah, I actually, some of the math people in here would know. Is that homogeneous degree 1?
Don't ask me.
Okay. So here's the design problem. If you really want to do this problem, you want to maximize how far away the absorbers are. You want to try and get a lot of mass out there, but you can't do that in a crankcase. So really the only thing, as soon as you maximize those two things, the only thing you have left to play with is this path. And I'm going to look at a 2-parameter family of path. This is not due to me. This is due to someone I'll mention later, but Victor Borowski, who was at Ford at the time and working with a guy. I got into this project long ago. I'll tell you a little story about that later. But essentially, the curvature of this path at its vertex tells you the linear tuning order, this n tilde. But I'm interested in nonlinear tuning, which means how the path depends on large amplitudes. And I'll give you a formulation for this in a second. But so the path selection, I'm looking at a point in this parameter space, and I want to know, how does the system behave? How good does the absorber work? What's its stability? And all these things as I pick this up. And the way I attack this problem is by averaging. But here's the path representation that's used. Essentially, you say the radius of curvature along the path as a function of s is the initial radius of curvature squared minus this lambda squared s squared. And this should have a squared on it right here, this n tilde squared, but that's the initial. So this is how you relate this curvature to the tuning order. It sets a linear tuning. This lambda, the nice thing about this parameter is that when it's 0, the radius of curvature is constant. That's a circle. But if lambda is not 0, it essentially gives you a family of epicycloids all the way out to when lambda is 1, you get a cycloid. Now, what are epicycloids and cycloids? I don't know if these things are taught anymore. Certainly people who design gears know about them, but this is what a cycloid is. And why is a cycloid interesting? Well, a cycloid is this path that's traced out like this. I don't need to describe it. But the reason this path is interesting is because it's known to be the perchristochrone, right? Which is the minimum time between 2 points, but it's also the tautochrone, which means if I start particles, a bunch of particles along on here, they'll all reach the bottom at the same time. In other words, the frequency of oscillation along this path is independent of amplitude. So what I'm doing is making a nonlinear oscillator linear. And this is how you can get away with large amplitude motions and convert this into essentially a linear problem for the absorber dynamics. But it turns out that that's for a uniform field. And of course, we're in a centrifugal field, which scales like the radius. It turns out that the tautochrone is an epicycloid, a particular one with this value of lambda. So once you set the linear tuning order, this is the value of lambda, and it's obtained by circle ruling on circle. And by the way, this solution of this is also the perchristochrone in this radial field. This was known to Huygens. So, and that's where it's used. So this tuning parameter is interesting. So basically, if I look at the tuning order as a function of amplitude of this thing, if I have things like this tautochronic epicycloid is flat, the tuning order stays flat, and all I do is change n tilde up and down. As I change lambda, you can get things like circles, which are softening. In other words, the pendulum frequency decreases as a function of amplitude. That's why this goes down, the tuning order goes down. And for things like cycloids, it goes up. Very, very classic. Now, the thing is that this was known. 1980, there's a patent from Madden, who is at Sikorsky Helicopter United Technologies. And he called this patent the constant frequency absorber. But he used a cycloid, and he even has this plot where he shows this curve, and he knows that it's hardening. This is the off-tuning as a function of amplitude. So he shows a circular path, he shows his cycloid, and he never mentions this epicycloid. So, but Ford back in the 80s tried to patent the epicycloid and it didn't fly. So you've seen this slide. Oh, one thing I do want to say is that when I get to the experiments, when I talk about epicycloids, I'll show this little icon, and when I talk about circular path absorbers, I'll use that one. But, so here's the equation of motion. Now I'm going to apply averaging. And averaging basically is just a way of taking, and to do this for these equations, I'm going to have to use a van der Waals transformation, but basically, it's right out of Guggenheimer and Holmes and other, and Hale's books and so forth. But basically, you have slowly varying right-hand side, and it's time periodic. And if you do a transformation, you can essentially remove the time dependence to leading order, and you end up with these. So this thing is really just the average of this function averaged over one period. And you get very nice things, for example, that fixed points of this truncated system represent periodic solutions of this under certain conditions, and various types of local bifurcations correspond. So the idea is you can, in these problems, what we can do is we can essentially average over the torque cycle and get equations for just the amplitudes and phases. So here's the absorber equations. And we do this transformation. This doesn't quite look like the right form, but we can transform this because we know the solution of this is a constant amplitude and phase when epsilon is 0. So if we transform to these amplitude and phase coordinates through this transformation, we essentially get equations that are slowly varying in amplitude and phase, so long as n and n tilde are close to each other. So we introduce an absorber tuning parameter. That's a design parameter, of course, this sigma. So n tilde now is related to sigma. And so the absorb, in terms of the amplitude and phase, you have these equations where these A's and this A and P depend on the sums of all the absorbers. You average over a period, which in this case is 2 pi divided by n because I have n cycles per crank angle. And you get rid of this theta dependence, and you have these new coordinates r and psi, which represent the average values of A and phi. Man. Yeah, see, this is an old version. I apologize. So what happens is the averaging, this amplitude, essentially just tells you this envelope, and inside there's oscillations. And so it's very nice for determining the absorber amplitude and so forth. So what I'm interested in is the synchronous response, where all the amplitudes and phases are the same. And essentially, so these guys all are in amplitude and phase, and the response is equivalent to that of a single absorber, dynamically equivalent in terms of torsion. But it turns out that, so you can analyze this as if it's a 2-degree of freedom system in terms of the response, because you have the rotor and you have the absorber, but when you look at stability, you have to look at the full problem, because the absorbers are talking to each other. So for the synchronous response, you get a classic Duffing equation. You can write down how this is the torque amplitude, this is the absorber amplitude, damping, nonlinear path parameter, E2. The form isn't important. The point is you can write down a closed form expression. And this is true for the weakly, the small amplitude, the scaled amplitude problem. But you can do a similar thing for you can find synchronous responses for the general path, for the tautochronic epicycloid, but it's a mess. So here's what their synchronous response looks like. So this is the absorber amplitude versus torque amplitude. This is the angular acceleration of the rotor versus torque. So when I say torque amplitude, it's the amplitude of this fluctuating part. And this is the reference where I blocked the absorbers. So if I pick an absorber linear tuning and then I change this lambda parameter, circles actually turn very quickly and become softening. In fact, this branch is unstable, and this branch actually is amplifying. So this thing has a very short range. If I look at cycloids, they're hardening like this. Epicycloids look linear in the absorber response, not exactly, but you get very good performance, but you hit a cusp. So these cycloids and epicycloids have a cusp, and that's what limits their motion. More important from an applications point of view is that a lot of times you're restricted on how much inertia you can have, and so you actually intentionally detune the absorber. So remember, this is changing n tilde away from exact tuning and increasing the tuning. And what it does is it essentially tunes the absorber away from resonance so that you don't get a sharper response. And so, for example, for circular paths, you can push out this saddle node bifurcation. You can push it out to larger torques. But you can see that you pay the price while you get a longer range of response, you get a higher torsional vibration. So this actually is I must admit that I'm going to talk about other instabilities that happen besides the saddle node. But this is very important to the car companies because they're trying to always balance the performance versus the torque range. And now it turns out that if you look at the stability of this problem, the averaged equations have amplitudes and phases. And if you linearize them about the synchronous response, the Jacobian has this form right here. And this Jacobian has this form very simply because this, you can think of A as essentially the effects of perturbations of absorber I back on itself. And B is the effect of perturbations of absorber 2, 3, 4 on absorber 1. And since the system has the symmetry and the response has the symmetry, you end up with this beautiful structure for the matrix, and it's block circulant. I'll talk a little bit more about that in a second. And the beauty of this is that the eigenvalues of this are actually given by A, and if this thing is 2n by 2n actually, because these are 2 by 2 blocks, I have n absorbers. I have two eigenvalues that are distinct, that are the eigenvalues of this, and then I have n minus 1 repeated a pair of n minus 1 repeated eigenvalues that are the eigenvalues of A minus B. Now it turns out that and so you can do this. I mean, in this problem, you can write these things down in terms of parameters and look at everything. The first thing is that I know that some people will be disappointed that there's no hot bifurcations. You don't get any traveling wave and stuff like that, so it's not as interesting as it might be. But you do get this classic jump saddle node bifurcation when these eigenvalues become 0, and when these repeated ones go through 0, you get symmetry breaking bifurcations, and those are highly degenerate because of the repeated eigenvalues. So the response in a typical absorber response curve looks like this. It's essentially absorbing here, amplifying here. When you're on this branch, the absorber is in phase with the applied torque. It's bad news. And so if you didn't know about this symmetry breaking bifurcation, you'd think that you could run out to here and then you'd amplify. But these non-synchronous bifurcations occur at various points on these branches. In fact, it turns out that if you make the damping small and the absorber detuning small, this point goes right back towards 0. You get essentially no stable operating range. So circulants. So there's a general theory of circulants. Normally I don't show this, but since it's an applied math seminar, I'll throw in a little bit more math. So a circulant is an interesting class of matrices. So you have, this is a 4 by 4 example, and you have generating elements V1, V2, V3, V4, and essentially if you push this over by 1 and take this guy and put it here, that gives you the second row, and you do the same thing, and you end up with this structure. So you have these 4 generating elements that generates a 4 by 4 matrix. And there's a beautiful book by Davis, P.J. Davis, on circulant matrices that describes everything I'm going to show you in a nutshell. But it turns out that if you look at the eigenvectors of an n by n circulant matrix, the eigenvectors, no matter what the generating elements, the eigenvectors are the columns of this so-called Fourier matrix, where if this W is the primitive nth root of unity, complex, you get all 1s, and then 1 W squared, W4. You look at these columns, these will be the eigenvectors of that n by n circulant matrix. And it allows you to do the following with this Fourier matrix. You can decouple this circulant matrix. You can essentially diagonalize it. And the eigenvalues are given in terms of, these should be the V's, sorry, these should be V's, V sub K's. And you can write down a formula for these lambdas in terms of the generating elements. And so this theory is exactly what allows you to do this, get these eigenvalues. Except for you need one more thing. You need block circulants. We have block circulants. So we need to look at matrices where you have, I'm missing a, where you have block elements. This is not the right slide, but anyway, the point is that if you have block elements, so C, the elements, the generating elements now are these capital C's. If you look at this direct product of the Fourier matrix if these guys are m by m, and you take the m by m identity and form this product, you'll block diagonalize the matrix, and you can form these blocks in terms of these. And that's how I get this. Actually, these are the 2 by 2 blocks. And so you end up with one that's unique, and then you end up with A minus B for all the rest of them. So there, again, if you want to see all the details of this, I highly recommend the book by Davis, which is where you get all this. Now the thing is that what happens at that symmetry breaking bifurcation is of interest. And it turns out that, for example, for basically you have a bunch of eigenvalues that go through 0, and there's a whole theory for this. But let me just show you that, for example, when the ending, if you have 4 absorbers, the first types of motions that you'll see have one lower order of symmetry. So you have 3 and 1 or 2 and 2. And both these come out of the same bifurcation point. And a big question is, are they stable? Is the bifurcation subcritical or supercritical? Our equations are so messy that we just do numerics. But basically, there's a bifurcation sequence that's expected. So if you have this represents the symmetry for complete interchange of 4 absorbers. The first instability will yield these 2 kinds of, and then the next instability, well, will both have this type of symmetry where 2 absorbers are identical, and then you have 2 others that are doing something different, and then of course you'll go to a place where you have all 4 absorbers doing different things. So this is what indeed you see. And let me first talk about this tautochronic epicycloid absorber. So now we have a set of n absorbers. They're all essentially linear out to large amplitudes, but they're coupled to this rotor. So I have this nonlinear coupling to the rotor, and it turns out that Paul Chow, a PhD student of mine from a while back, I'll tell you more about history in a little bit at the end. These papers are old. But essentially, what happens is you can prove in that case that the bifurcation is a supercritical bifurcation, and then this point in the space of absorber amplitudes throws off an invariant ellipsoid. And at the vertices of the ellipsoid are all of this class of responses with this class of symmetry. And it turns out that you can examine the stability near the bifurcation point, and the only one that is stable is the one where you have one absorber doing its own thing and the other n-1 doing mutually synchronous. That's the only one that's stable. And so what you see is the absorber amplitude, as you drive the torque level up, it goes unstable, it throws off this solution branch, and the thing is that this absorber, its amplitude starts to grow very rapidly. And that's bad news for vibration absorbers because it's going to start hitting constraints and so forth. And in fact, in this example, we can show exactly that this bifurcation point scales in such a way that as the damping goes to 0 and the tuning order goes to n tilde goes to n, that goes right back to 0 amplitude. So this is something that you have to worry about. So here's some numerical simulations. And the solid and dashed curves are solid is stable, dashed are unstable. Results from averaging. This is for 4 circular path absorbers. These green triangles are symmetry breaking. These purple diamonds are jump bifurcations. And what I'm showing right here are the S2 cross S2. I'm going to show you more, but this is enough for one diagram. What happens is these bifurcations coming off here, these are the ones I'm interested in. There's also one here. Well, actually, they come off, and they're subcritical. And there's a range over here where they're stable. So you have 2 absorbers at this amplitude, 2 absorbers at this amplitude. And they coexist with the desired synchronous solution. And what's even more dramatic are the S3 cross S1 responses, because this unison response, which is nice and stable, by the way, these are simulations, these dots of the full nonlinear equations of motion. And we only show spot ones down here. We're mostly interested in these. But this is the single absorber, and these are the 3 absorbers. And this single absorber, actually, its phase is all wrong. It's making these absorbers work harder. There's less inertia working, and the phase in this guy's wrong. And so these 3 absorbers. But the point is that in this torque range, back in here, you have a stable unison response that's decreasing vibrations, one that's amplifying, plus you have S3 cross S1 and S2 cross. You have all this nightmare and all the permutations involved of these absorber dynamics. And they're seen in experiments and in simulations.
How does one get on that disconnected range?
Initial conditions. So going over, you bump the system and it could go to any one. In fact, in a perfectly symmetric system, of course, there's all kinds of permutations of those.
Can I ask a broader question?
Yeah.
Why do these things have to be mechanically decoupled from each other? Why can't you, I mean, is there a reason why there's no mechanism that you're not considering?
To lock them to be synchronous.
Yeah.
Okay, so here's, you could consider that problem. But in reality, you've got a crankshaft inside a crankcase. Any mechanism that does it is going to be a mess. It's going to add friction. It's tough. So in reality, these non-synchronous responses, the way they avoid them in practice is by detuning, which I'm going to show here. So if I look at, this is say for n equal 1.5, this is like for a 3-cylinder engine. And this is the fluctuating torque order. This is the tuning of the absorbers. It turns out that this non-synchronous threshold looks something like this in this space. So we're stable, the synchronous motion is stable here and unstable here. And so what they do is they tune absorbers to 1.51, and then they know over their entire torque range up until the absorbers hit the cusp. You're not going to see this kind of thing. That's something that they actually take into account in their designs. Now it turns out that Bruce Geist at Chrysler and I did a general analysis. So this is that parameter space where this is the linear tuning order and this is that nonlinear parameter. So this is these are detuning circles. This is detuning tautochronic epicycloids, and this is detuning a cycloid. The gray region is where you have a non-synchronous response. So you have eigenvalues of those repeated eigenvalues you have are positive, or some of them are. And this is the jump. So a circle actually will undergo jumps. But if you start to detune negative, here's the thing, that if you make a perfectly tuned epicycloid, you still have this instability. So the way they think about these designs is that they actually off-tune in this direction. And one reason is that when you go in this direction, you actually increase the torsional vibration level. I should show contours on here. Torsional vibration. Basically going this way, going nearer the center, you decrease. Going this way, you increase, and going this way up to a point, you decrease. But the point is you get as close to this instability as you can, but you off-tune a little bit linearly. And I must admit that generally, I'm not giving away big secrets here, but Ford is essentially doing here and Chrysler is doing up here. So we have an experimental test facility here. Some of you will recognize this guy. This is Brian Feeney, PhD from Frank's student from about, 89, 90, something like that. He's my colleague. Before, and this is Alan Hatta, who's retired from MSU. Alan built this experimental rig, and he's retired, so Brian is, they try and, I do know how to run this rig, but Brian's the master at it, really. So these are absorbers. These are our absorbers with rollers and stuff, but you can't see much. But there's encoders on here. We can fit up to 4 absorbers. We have a motor. We can control all kinds of, we can mimic things like cylinder deactivation events, things you can't, and we can measure what the absorbers do, which is very, well, actually, none of the car companies now. They build an engine, and they run it, and they figure out what the torsional vibrations are, but they don't know what these absorbers are doing, other than by inferring it from what the other signals do. So we can do all these things. So you have a strobe light here. It's very nice, so you can watch it. And we've actually had the vice president of Chrysler, the powertrain vice president in our lab before looking at the strobe light, which for someone with a degree from TNAM, it's like real engineering. So we have these kind of absorbers. These are simple pinned. This is just a way we configure it, but these are simple pendulums, single point suspension. They can swing back and forth. These are not what we use now, but we did these for a while. These are steel bands that wrap on these cheeks. This is the way Huygens designed clocks, right? The constant frequency. He put cheeks on a mass and a string so that you follow a cycloid. And these follow an epicycloid. And so we spin these things up and measure things. So I'll just show you some experimental, typical things. These are things you can't do in an engine. We can change the order of excitation and look at the rotor acceleration, and we can figure out where the tuning order is. This resonance is the coupled mode resonance for the absorbers, and this is one absorber. But you can't do that with an engine. So this is very useful for design. This is an epicycloidal absorber, one absorber, where we do a torque sweep now, and we change the excitation order, and we have analysis, and Newton's laws work. The only thing that really is hard to model here is damping, and it's light, so it doesn't matter. But the absorbers, you can see max out at the cusp. And so we get this, but the more interesting thing are these motions that we see. So this is 4 circular path absorbers. Student Tyler Nestor did these experiments as a master's thesis about 10, 12 years ago. And we're very close to, so the tuning order for these absorbers is 1.31. You're driving them very close to this. And the absorbers are slightly over-tuned. And as you change the torque level, you see things where you have 2 absorbers doing all the work and 2 absorbers essentially at 0. Here, you decrease the torque a little bit, and you see 3 and 1. And these are different these have the same symmetries, but they're different than the ones I showed before because the other ones had all the absorbers doing something. But this is a picture that I don't have a great handle on, but we observe it experimentally. It's interesting because I want to show people in here who think about coupled systems, coupled oscillators and resonators. But these 3 curves, this is the absorber amplitude versus torque level, as if you had only 2 absorbers, if you had 3 absorbers, and if you had 4 absorbers. And as you increase the torque level, at first, well, we can't get any signal until the absorbers start wiggling, but the first thing we see is 2 absorbers not doing anything and 2 absorbers essentially following this line. Then we get into the next region, and there's a region here where the absorbers, one absorber stays inactive, and the other one starts, this triangle becomes active, and then they follow this 3 branch for a while. And then there's another transition where this absorber becomes active, and then they end up following the 4 branch for a while. And it's completely repeatable. And our analysis, we've messed around with this. And I will say that this difference in detuning is bigger than we've measured the orders of all the absorbers, and this should push us out there. So this is something that's still curious to us. And these are old data, so I still have things to think about.
So when you simulate that in your model, you don't see that behavior?
And the only thing that I can say is that probably within machine tolerances, my only guess is right now is that the differences in friction and the absorber damping cause this. And we play around with simulations, but we put dry friction in, for example, but these are wiggling a little bit, so it's not really dry friction.
In your model, have you tried to put in slightly different masses or different?
Yeah, different paths.
Yeah.
But I think we need, again, Tyler measured each individual absorber dynamically to get its tuning order. And so we simulated those. So there's something not right in the model compared to our experiment.
And n equals 4 absorbers has more resonant terms than the normal form. Are those included in your model?
So you're talking about like the normal form for the bifurcation and all that? Okay, so, John, we don't even work, these equations are a nightmare. So what we do really, in the average equations, we keep whatever comes out of the averaging and just solve the average equations. We don't try to do any transformation to get rid of any terms or anything. So whatever was in the full equations and survives the averaging is in there. Yeah, so I kicked around thinking about trying to figure out what the coefficients in the normal form, but it's just a nightmare. Maybe, I think, if I were going to do it, I wouldn't do it for this system. I'd do it for a set of coupled Duffing oscillators, which is an equivalent system, globally coupled Duffing oscillators. I think that would be more tractable. This circular path, well, actually, so yeah.
But if you had dry friction, if one of them is in the lock mode, then you effectively lose one.
Yeah, but these are wiggling a little bit. Now maybe this is just some sliding from dry friction, but we had a student who looked at the model of dry friction, master's thesis. He didn't want to get a PhD on an interesting problem, but he put dry friction in our simulation model, and he still couldn't get them to do this. So
Is there hysteresis in those plots? Or are they reversible?
they're reversible.
Are they rolling?
These are single point suspension.
Oh, single point.
These are single point.
Because rolling, then friction is important. So
Oh,
whether
my
it's rolling
goodness.
or not rolling.
So
Rolling
in our rig, we want to get rid of gravity because we can't run at very high RPM. So we worry about rubbing. These things actually fit on here like this. So we use self-centering rollers to lift it off and make it so that it moves like this. And actually right now we have a student working on the problem of gravity because it turns out that for engine speeds and engine sizes, gravity effects become on the order of 5 to 10% of what the applied torque does. And it's a really interesting problem because gravity has a very different excitation essentially it has an order 1, but it's direct and parametric, because this thing's going around like this. So even in the linear problem, you get very interesting combinations of harmonics, because you have this driving term that's affecting all the absorbers the same, and you have the gravity term which affects them as they go through this field. That's an interesting problem separate. But anyway, so we worry about gravity too. So automotive engine tests. Real Ford crankshaft with absorbers. And they machined this thing. And we're gonna test it down here at idle. Here's Alan Haddow's garage. This is Tyler Nestor. The reason I show this picture, there's 2 different trucks. We could not lock the absorbers. So they gave us a truck that we could deactivate. Well, this is the truck with the absorbers. This is a truck without absorbers, but what we did was we disconnected the fuel injectors, and I'm wearing a Cornell sweatshirt there, by the way. And in Alan's garage, we ran this set of tests, and we followed Ford protocols. I mean, you know, we put accelerometers where they put them and everything. So I'm going to show you the ZC track. This is the acceleration with absorbers and without absorbers on the ZC track, which is one they worry about. This is the power spectrum. This is order 2 when it's running in 4-cylinder mode. So we deactivated 4 of the cylinders. 2 orders of magnitude drop at second order. Worked beautifully. This was published in the Society of Automotive Engineering Journal. When I've shown this picture before in car companies, I've had people say, "Oh, that can't be." And but anyway, that was 10 years ago. Now they're believing it. So here's some work that's ongoing. I really apologize. I'm missing a picture I wanted to show you.
We wouldn't know that if you didn't tell us.
I'm going to tell you. I'm going to look for it because it's. I'll tell you the history anyway. So here's what we're doing all these things with car companies. Mostly we're working on this torque converter lockup and legging out with 4-cylinder engines. Cylinder deactivation, we did a little work with Honda. But effects of gravity at low speed, orders 1 and order n, but they come in very different ways because the order n excitation affects all absorbers equally, whereas this guy is a cyclic type excitation. Here's an experimental result of 2 absorbers that are about as identical as we can make them. And we start them up, we essentially are running the rig, and we suddenly turn on, so we're running at constant speed, and we suddenly turn on the excitation. And you can see that the transients, these kinds of things happen when you have these kind of systems with degeneracies. You get very different transients. It eventually settles back down. But these kind of problems are all related to the imperfections, I think. Here's the other thing we're interested in with a former student, Jimmy Issa, not of mine, but I was on his committee. He's looking at the problem of Duffing equations, where we look at, he's got essentially complete bifurcation diagrams for zero damping to try and describe where all these non-symmetric terms come from. And I know that there's stuff like this in the math literature for coupled oscillators. These are coupled resonators. And they look similar though. You get all these connections, this underlying curve, these bifurcations. He's just now working out the stability for the 3 absorber case. This is what it looks like. It's a mess. So in other words, we're trying to go to not just showing this level of symmetry, but figuring out all the solutions in that problem. And I have a PhD student who's just starting on this problem. This is an old picture, but what's true in a crankshaft is that you can have several degrees of twist. So these are actually pendulum absorbers. This is an old paper from here to here. And so the rotor's not rigid. So the question is, when you have a stiff, but not infinitely stiff system, and you hang absorbers at different places, and the torques are at different places, it turns out that if you go back and look at the old papers in these problems, not Newland considered a rigid rotor, but there's work on flexible rotors. It turns out that they actually recommend that you undertune the absorbers, where everything that we see for rigid rotors says you should overtune the absorbers. And so we don't really understand which way to go when you're doing this model and where the transition might be. And by the way, everything I said about tuning was based on linear theory. So here's my collaborators. Alan Haddow, Brian Feeney, I showed you their pictures. A whole string of grad students over the years. For how many years, I'll tell you in a minute. Undergrad students. We always have an undergrad hanging around, working on. These folks have all gone on to do great things, grad school and so forth. Chrysler. Our main guy is Bruce Geist. Since I'm giving applied math talk, Bruce Geist has a PhD in applied math from RPI. And he is Chrysler's in-house applied mathematician. He gets to work on all kinds of things, including dynamics with us. But he is a great collaborator because he actually gets in and figures out what work. He actually collaborates. We have weekly phone conferences with Bruce, and he goes home and plays with. He says, "What about if we try a different kind of path?" And he goes home and plays with different paths. And math. At Ford, these guys, I'll tell you about. Victor Borowski got me into this problem 30 years ago, actually, to this month. Victor is still kicking around, and he's retired down in Dearborn. I saw him. These guys are taken over. And Ford is interesting, different cultures at companies. Because Ford is very open, but they're tighter with money. Chrysler actually, because of Bruce, is more willing to fund us. But on the other hand, man, they don't share anything. I've helped them design Crankshaft, and I say, "Can you give me some data to show?" No, we can't do that. But anyway, Honda RD, we did one small project with them. So the thing that really drives this is the National Science Foundation GOALI projects, grant opportunities with liaison with industry. And so with Bruce, with this right here, this gives you like 3-year lumps of funding, so you can actually have students work on it. Ford and Honda is like, oh, a year or 6 months here or there, and they sort of fill in the gaps. Now Victor, so what happened was, I gave a talk early in 1984 about nonlinear oscillations at Oakland University, and I remember a guy recorded a tape recorder, and about 3 weeks later got a call from a guy named Harry Denman, who's a physicist, retired now at Wayne State, and he said, we got this nonlinear oscillations problem that we need help with. So I went over to Ford, and Victor, it turns out, did his master's degree with Harry Denman, and Harry was working as a consultant for Ford, and Victor introduced me to this problem, and they actually, they had a very, I would say, elementary level understanding of nonlinear dynamics, and so they started including me in things. And this is how it started. And then I started peeling off some of these more fundamental questions that I was interested in, and got an NSF grant. And for a long time, the car companies were just, in fact, we built that experimental rig trying to get them interested. As I learned from Frank, have an experiment. Have something you can show people. Industry doesn't care about equations. Have something to show them. So we built this thing, Alan built it, and we have people in, but what really drove this, as far as the car companies, is the fuel economy link. But it's a fun project, and Victor, in preparation for that lecture that I gave in Portland, I went down, and my wife and I went down and had dinner with Victor and his wife, because I've known him a long time. And Victor lives in a house that was built for Henry Ford's brother. And that's the picture that I wanted to show you. So, but anyways, me and Victor in front of the William Ford house, and Victor he actually took this house, which was going to be demolished. It was in a park in Dearborn, and he bought it for $1. And then it cost him $400,000 to move it and put a basement under it and everything. But it's a beautiful arts and crafts home, and Victor still lives there. And when I go down to see him, he's playing with the absorber equations in Mathematica. He's still going strong. But anyway, so this is, and so my history with this has been a long time, and it just seems like every time I turn around, the car companies are calling, and I think of some new thing to do, and I don't know, I'll probably retire, and this thing has been a theme. I do other things, but this one has been a constant theme for 30 years in my career. So thanks for your attention.
Thank you. So you have been a professor at all these different Michigan campuses, and Detroit happens to be the place where all these car companies have their labs and factories. Is that a coincidence? Somehow is the geography an important sociological feature?
It made it easier for them to find me. But for example, when the way Bruce found me was on the internet. He had a colleague who said they were interested in torsional vibration, and they were looking at things, and Bruce had a colleague who said, hey, these pendulum absorbers are interesting, and so he was, looking online. This is about, I don't know, I guess it was 8 years ago now, Bruce found me. And he called me. So I think if I was working at here or Iowa State or somewhere, he would have still gotten involved. But the point is that it's really nice because we can take a band full of students down there and stuff. But it's not, so it's convenient, but I wouldn't say it was essential.
Are there people who aren't in Michigan who are working on these things?
On these, work with the car? Oh, yeah.
Any car problem.
Yeah, oh, like for example, General Motors has very close connections with, I think, Ohio State and Purdue. You know, basically, they do like to focus in the Midwest, but not exclusively. Stanford, for example, has a very active automotive engineering research. So,
Who is the Parker on your list of?
Pardon?
Parker?
Oh, Rob Parker?
Yeah.
Yeah.
Where is he? Who is
He is now the chair of mechanical engineering at Virginia Tech. He was in Shanghai Jiaotong for 3 or 4 years as some kind of a dean of international something or other at Ohio State before that. He's actually,
So he's the gear guy.
yeah, he's the gear guy, and he got interested in these problems. So he had this student who's now he did a master's degree with Rob at Shanghai Jiaotong, and is now a grad student at Berkeley. But anyway, he had the student work on some absorber problems, like and mostly linear things. So for example, these absorbers, of course, affect the shaking forces. So now if you put these degrees of freedom on, and even tilting, you put them in different planes. So we looked at with Rob, we looked at a lot of the linear response for different degrees of freedom that way. And it turns out that if you take if you have in engines, because the piston's going up and down, like in a 4-cylinder engine, you actually have what's called a secondary shaking force. Makes the engine go like this. They put counter-rotating weights, balance shafts to counteract it. But it turns out that if you take absorbers that are tuned to order n-1 and n+1 and put them in the rotating frame, you actually get a rotating force at order n. And so you can counteract that force. You add a little bit this way. And this was known, I learned about that from Victor Browski because he said, and this is known a little bit, but he said that when Den Hartog visited, he brought Den Hartog to Ford in like, I don't know what year.
You should tell people who Den Hartog is.
Oh, Den Hartog is, so Den Hartog was, he's like the father of modern mechanical vibrations. He wrote a book in the 30s, but Den Hartog came to this country, and if you don't know his name, maybe you know Timoshenko's name. Den Hartog and Timoshenko were together at Westinghouse, and they're two really, giants in the field of mechanics. Timoshenko in solid mechanics and Den Hartog in dynamics and vibrations. Well, Den Hartog actually wrote the first paper about the nonlinear response of these things, where he essentially said, look, if they sweep through large angles, you're going to soften them, so you better overtune them. In fact, this guy Newland I showed again, he was Den Hartog's student. He's now a retired professor at Cambridge. And Newland actually wrote a paper all about how you detune circles so they work well. And then Madden, essentially in 80, went and did this path thing and so forth. But anyway, Den Hartog, Borowski brought him to Ford back in, I don't know, I'm going to guess it was the late 60s, early 70s. And Don Hartog said, hey, you got that secondary shake force problem. You should put some absorbers on tuned to order n+1 and n-1. Ford tried it, but it turns out that you need such massive absorbers at those orders to take care of the shaking of the block that it was really, you had a little crankshaft like this and it had absorbers. Anyway, so Rob Parker and I worked on those kinds of problems, the linear response of those things.
Can you say what is different in any car today or in the future because of the stuff you're doing?
What's different, you probably won't notice it, but what'll happen, except
But
when
is your stuff in cars today?
My stuff is not. So you can buy, there's certain Mercedes-Benz and BMWs you can buy. So you have a crankshaft, you have the torque converter for an automatic transmission. For a manual transmission, and in lots of cars there's something called a dual mass flywheel, which is nothing more than an inertia on a big spring. It can have large travel. It essentially softens up this stuff from what's downstream. They put these things on the dual mass flywheel just to smooth out, but they're very small inertia, and they're marketed by a company called Loop. So you can buy a car with these at that point on the powertrain, but not on the crankshaft. The crankshaft allows you a lot more inertia, a lot more aggressive tuning, and so what will happen is your car will run at lower RPMs, higher torques. The engine we're working on with Ford is a 1-liter, 3-cylinder engine EcoBoost. 1 liter and 1.5 liter, turbocharged, and that thing just shakes. It's just a vibration nightmare. To me, it's a vibration dream.
It's interesting that for the students, the history of Duffing. Duffing started working for the auto engine company. that's where he got into nonlinear vibrations, and he wrote his. So now you've got Steve working for automobile companies with multiple Duffing oscillators. So it's like there's a history, and it comes around, and you still got the same, only more complicated problems. But Duffing started working in automobile companies on this.
Yeah, I did find one of my slides. This is hardware. This was for a 3-cylinder minivan. My last slide actually showed essentially, John, it showed I can't explain it, but anyway, it showed essentially a picture of a minivan, and the minivan. A lot of this work for Ford and Chrysler. They're getting money from the DOE. In fact, I'll tell you a funny story about this picture. This is a Chrysler crankshaft. Chrysler never showed me this, well, didn't show me this picture. Ford sent me that picture and said, do you know anything about this? And I said, yeah, I know a lot about it. I said, where'd you get it? And they said, oh, from DOE program review. And I told the guys at Chrysler, oh my God, my bosses haven't let me show you that picture, and they're parading it around. But anyway, so this is a Chrysler, but this was a minivan we did. This is that EcoBoost engine. This is the crankshaft that I built with Victor, well, I helped Victor design back in the 80s.
So were you allowed to tell Ford what you knew about it? Did you?
Well, Ford was looking at this thing, and they're saying, what, you know, they were blowing it up and looking at holes. I said, guys, I just, and the reason I can get money from both of them is because they know I don't talk.
Yeah, that's what I'm saying.
So have you played around with using 5 rather than 4 vibration absorbers?
This one you see has 4, but the prototype that they built, actually, they don't show them here, but there's more absorbers. There are actually 7 on this crankshaft, the one that's built in a minivan. By the way, what I want to say is,
But
Chrysler's going to drive a minivan with this 4-cylinder turbocharged engine for a DOE program review, and right now it's getting 41 miles a gallon for a town and country minivan. That's pretty good. But anyway, go ahead. Sorry, John.
So are the 7 are displaced at angles of 2 pi over 7, or?
No,
No.
no.
So I was curious because of the symmetry in the system in your test facility.
Yes.
Can you go one that has 5 instead of 4?
Oh, yeah. Yeah, we right now, Chrysler is, we designed up in Chrysler for our rig, we're building a ring with a bunch of holes spaced in weird ways so we can go any number up to 6.
But these are in different locations on the.
That's right, so what we can do is we can mimic a rigid rotor, a rigid crankshaft on our laptop.
But I think the small flexibility is something we can't neglect. Because years ago, it's like everything comes around. Years ago, my first job was with the Navy, and one of the problems they had with aircraft carriers were torsional vibrations.
Yeah. What?
And certainly the car companies had torsional vibration problems in the early days.
Yeah, I agree. And so that's exactly what our next project with Chrysler for this year is to, we've looked at the linear theory. It's actually very interesting because you have order tuned elements, constant frequency elements, which means you get eigenvalue varying. And it turns out that the undertuning business actually allows you to design the absorber to shoot the gap between the eigenvalues and not have a resonance. Because anytime you have an order excitation line that crosses a natural frequency line, you get a resonance. In our models, we can shoot the gap and avoid the first resonance, the first low-speed resonance. But we have to undertune, whereas everything we see nonlinearly overtunes. So that's exactly what we're going to look at, the nonlinear version.
If you have spatial oscillators, you'll probably get stop bands and pass bands.
Yeah, the other thing is that the absorbers aren't the only thing that are distributed. The torques are also distributed, right? And so you're getting these pulses once every 2 crank revolutions at different places. And that's what we have to put in the model also. So that'll affect
I'm thinking of transmission line models.
Yeah.
Where you have LC, LC,
Yeah.
LC, LC. And when you look at the spectra, you get stop bands and pass bands.
Right.
And maybe that's something to do with your the locking that you get there.
It could be. The one interesting thing about these order tune things is that when you have an engine with N cylinders, 4-stroke engine, the excitation order is fixed. That's just it. Now, that's not Exactly true, it's dominating. It has some other harmonics, especially if you have cylinder misfires, you get things at half words, but they're very small. When it's running in cylinder mode, you get a huge dominant harmonic at one order. And then when you build the hardware for the absorbers, they're tuning ordered. So the frequency ratio in these problems is essentially fixed. You don't think about, what happens if I send different frequencies in, do they come out or not? Everything, once you build the hardware and you put it in an engine, it's like you've got this fixed frequency ratio. The only thing, the most important thing that you vary is the amplitude of the fluctuating torque, which scales, there's a non-dimensional parameter, which is that torque divided by essentially scales like 1 over omega squared. You get a nice non-dimensional parameter that tells you what the non-dimensional torque is, and varying that is really what an engine sees in steady operation. That's one reason people, when I show this in engineering, they always say, well, how come these aren't in cars? They've been around the light aircraft forever. And the reason is that the car companies are afraid because of the transient environment. Your airplane, what does your engine run at? Like 2,300 RPM all the time, right? Virtually. Something.
I know where to put the key in.
But anyway, so in aerospace, like helicopter and light aircraft, they run at pretty much a constant RPM. The auto, it's all over, up and down. And
What about hybrids? Are these ideas useful for hybrids?
I don't see it really.
Because then you turn the engine off.
Yeah. Actually, one of the important, related to hybrids is they worry a lot about these things during startup and shutdown, because they say, okay, start-stop technology, right? You buy a BMW now and you come up to the traffic light and it stops, even if it's a regular gas engine, right? So what about these things? So, and we had undergrads work on essentially centrifugally activated catch. It's a nice undergrad design problem, catch release devices, so that when the thing goes below 200 RPM, it catches the absorbers and stuff like that. We had a student build one and test an our rig, things like that.
Fantastic.
Oh,
More questions?
Yeah, I was just interested because almost all of your stuff is sort of regular crankshafts and pistons, and then you add this thing on.
yeah.
But back in the 30s, there were all these weird ideas, right? There were de saxe things, which may have been mainly for friction, but might have spread out the torque. There were working beam crankshafts and so forth. Any
Oh,
of those
yeah.
things, are they totally impractical?
Oh, these other designs?
Yeah.
Oh, I mean, our engines group at MSU was looking at one of these old engines where the pistons come together,
Yep.
These kind of things, a Junker engine, I think it was, or something. I can't remember, German's invention. So, yeah, those ideas are resurfacing, because they have
Nice to
great
see the
efficiency.
three-cylinder engines coming back again.
Yeah. I mean, that's one-cylinder engine.
Is there people working on this a dumb way?
1 liter, sorry, not 1 cylinder.
A dumb way instead of a smart way, where you would just say you got Newton's laws and you do simulations and you have some general vague design idea and you have 2 or 8 parameters and you just do massive simulations. Do people do this, or do you have to be smart to do this kind of design?
Well, you don't have to.
No, but it just seems to me you're doing very advanced, subtle stuff, but in the background there's people's MA and lots of
Yeah.
people do
Well, that's what
So-
Honda gave us a contract last year, and they could have done everything if they had just read our papers. I told them that.
Well,
But
what's
they
this
don't
paper?
have the manpower to try and figure it out, and we have codes running. In fact, Ford now, I'm gonna get a check because we actually licensed our software to Ford so that they can run it, because we used to do runs for them, and they said, well, why don't we
This
run it?
simulation software, or
Yeah,
your-
no, it's a simulation and predictive. It'll predict these response curves and stability.
but what about just designed by simulation?
Designed by simulation, you can do it, yeah.
But you can do it or can't?
Well, you can, but the question is, they don't even, so you want to test a bunch of different engine operating conditions, you've got a bunch of different parameters that you might want to try.
And you let the computer run all night?
Yeah,
run
you can
genetic
do it. You
algorithms,
can just
something
crank
like
out
that.
response curves like crazy for different parameters.
Well, a
Sure.
related question. Are they capable of deriving the equations of motion?
Yeah, Bruce Geist actually is a very smart guy. He not only, so here's an interesting design problem. You take this absorber mass and it's got holes. And you're changing the tuning, you're changing the holes and the pin. By the way, you have to really account for the dynamics of those rollers, because the tuning is so sensitive to the linear tuning, and those rollers move on half the path and they roll without slipping, which we verified experimentally and stuff. but you have to account for those. But anyway, the point is that as you're changing all this, you're changing the center of mass, you're changing the tuning. So actually, to design an actual mass and the cutouts is like an iterative process. Bruce wrote a code that does that. He says, okay, I want something that's a cycloidal path. You see what I dream about machine winners. But I want a cycloidal path tuned to order 1.51, and this thing will evolve and come out with, then he can send it down to the machine shop. So I mean, he does that, and he knows, he's got his own simulator. In fact, when we started doing the gravity problem, he goes, oh, I already have that in my simulation. I've seen, he says, yeah, we see some weird stuff with gravity. Down at like 500 RPM, which is a very low idle speed.
I remember Andy saying that no one had derived the correct equations for a bicycle. After 100 years of screwing around with it, that's probably mistakes in all of these codes.
It's a little different than that. It's sort of, it's not, my saying that is different from the codes, because the codes work kind of better.
In which codes do you think there's mistakes? The ones I sent to Ford? They're benchmarked.
All of them.
Yeah.
No, he said there are massive things, well, maybe everybody's not interested in this, but there's a whole community of people who do dynamic simulators.
Yeah.
It's a large community, and there's two communities, like the engineering community and there's the computer graphics like community. And I think all of those people know the equation, F equals MA and M equals I alpha. They know those equations well, they can simulate them accurately and so on. The problem is when you want to do some special problem and not have sort of general equations in motion that you throw at the computer, but you want specialized equations in motion, and then you have to know the technical details in some way that maybe those people don't know and can't do.
See, a
So
Ford,
they could do a bicycle badly with one of these giant simulators, and it would be correct in some sense.
yeah, using
But
atoms
you
or
only get
something.
2-digit accuracy or something like that. If you want to have like just minimal coordinates and 7-digit accuracy, that's what people haven't done for 100 years.
Yeah. I mean,
That
actually,
really
the
works.
hardest thing to model in these is the damping, friction. This thing's whipping around in your crankcase, there's an oil mist in there, things are rubbing and rolling, and geez, who knows what happens there. I don't even want to think
Steve,
about
this
it.
is really fantastic because the dynamics community here are largely theoreticians, and it's fascinating to see you using a lot of these ideas of bifurcation and symmetries, for example, and group theory in a problem that's practical. So let's give them another hand, and you can ask questions.